Hey, welcome back. So I thought we'd have a little bit of fun today and show you how you can actually fine-tune your own model on Apple hardware using Apple MLX. In fact, what we're going to do is do a little bit of inspiration from inference or test time compute, and we are going to teach the model to be able to perform calculations. So, that famous question, is 3.11 bigger than 3.9? Well, one way we can actually solve that is by using a calculator to solve the problem. And the way we will do that is we will train the model to use the calculator or actually generate a calculator script. And that actually is the basis of inference time or test time compute, which is rather than training for the final result, i.e. the sum, actually training it on the process. Now, fine-tuning the model is fairly complicated. And the reason it's complicated is there's a whole set of things you need to take into consideration. Which base model to use, how diverse the data is going to be, and because models can forget tasks, how to use things like mixers, etc., to be able to remind the model how to perform tasks that it used to do, and also what the impact of the diversity of data is going to be. So it's going to be a bit of a fun ride, and with that, we're going to get started. So the first thing you need to do to get started is have Apple's MLX LM framework installed onto your machine, and you can do that just by doing a pip install MLX LM. Once that's actually installed, you can use a couple of command line utilities to actually chat with the model as well as fine tune it. So in this case, we're going to do mlxlm.generate. And again, this is a kind of non-chat at this point. It's just kind of prompt completion. And if I type in something like --prompt, and we will say hi, then you'll see it's going to work. Now, it will download a model for you there, but you can see there, hello, it's nice to meet you. Is there something you can do, or would you like to chat? Now, underneath the hood here is actually using a model called Llama 3 to 3B instruct, and it's been sort of quantized down to a 4-bit model. So it's actually a tiny model in that sense. And that's one of the reasons it's actually so fast there. You can see it's running at 158 tokens per second when generating, and that's because it's a very small quantized model and it's a 3 billion parameter Llama 3.2 model. Now you can specify the model that you want to use. Today for fine tuning, we're going to use the Qwen models, mainly because Qwen models have lots of different ranges. So they've got a 500 million parameter model. They've also got a 1.5 billion parameter model, a 3 billion parameter model, and a 7 billion parameter model. And it's actually quite useful to use the same model range to show the differences of the impact of size when you're fine tuning. So it's fairly easy to put your model in there. So I'm just going to do mlx underscore lm.generate. This time I'm going to have a little bit more of a complicated prompt. So we're going to say, tell me a limerick about cheese. And then, of course, we are going to specify the model. So in this case, we're going to do model, and it's going to be Qwen, and it's going to be Qwen 2.5 coder, and it's going to be the 500 million parameter or the 500 million parameter instruct model. Now, just in case you're wondering what the difference between an instruct and a base model is, the base model is a model that has been through pre-training, but it has not been fine-tuned for things like alignment for chat. So when you're working with a chat model, for example, that is usually the instruct model, and that's what's going to be aligned for safety and all that sort of thing. We're going to use the instruct model just because all of that alignment's happened already, and we're only going to be putting a few samples above there. Again, if you were building your own chat model and putting all your own chat samples in there, then you might prefer to take a base model in that case. But today we're just going to use a nice little instruct model. And again, this is a tiny model that I'm using here. It's a 500 million parameter model. Now, as you can see there, it's not done a very good job at understanding the limerick, and that's because it's a tiny model there. I can ask it other questions. So if I change the prompt to something like, what is the capital of France? And you can see it can do basic kind of Q&A. It knows what the capital of France is there. And it can do sort of questions about, and as you can see, it came back with an answer there. It's not a particularly accurate answer. It thinks Ada Lovelace is American, etc. But again, it's a 500 billion parameter model, so it's not going to get great answers there. If I was to ask the same question, but this time of the 7 billion parameter model, and again, remember I'm using the Qwen 2.5 coder model here there, ask that same question here, who is Ada Lovelace, and you see suddenly Ada Lovelace has changed from being American and is now an English computer scientist. And similarly, if I ask the same question, tell me a limerick about cheese, it's going to do a better attempt there. So it's got the limerick structure there. Maybe the rhyming's not as good as you would expect. Cotswolds, bold, and smile isn't really rhyming in that sense, but it's got the basic structure of a limerick. And again, if I went up higher models, then it's going to do a better job of that. So that's probably the first thing to realize when we're going to fine tune a model, is depending on the model that we want to use is going to be dependent on the quality of the output. Small models will be able to perform maybe sort of pattern matching type tasks and basic tasks, but it's not going to do anything that needs complex reasoning. However, as I'm going to show you, it is perfectly capable of performing a calculation. Okay, so we've got a base understanding of the models, but now what we want to be able to do is go on and fine tune those models. So in this particular case, so I brought up VS Code for a second, and I'm going to use the folder calculator non-diverse at the moment. So what I mean by non-diverse outputs is, you see, I'm just given the answers always as the same. The result is, the result is, the result is. Now, in this case, we're going to teach the model to perform a calculation. So if I ask it to add two numbers together, if we come back to Qwen for a second there, and let's do this with the 500 million parameter model. If we say something like, what is 25 plus 5? As you can see, it's going to be able to do those basic mathematic functions. But if I ask it a more complicated problem, so let's say I just stick a couple of numbers in here like this, maybe change that from a plus to a multiply, then it's going to make an approximation. So it's going to give you a big answer there, but it's not the right answer, as we know. And that's because LLMs aren't very good at math and they do approximation. What we really want it to be able to do is, rather than sort of taking its own guess of what the number is, we want it to perform this calculation. So that is what we are going to do with the fine tuning of this model. So we need to create a data set in this sense. So in this case, a data set is going to be a JSON-L file. Now, because we're not doing a chat format, we're just doing generations at the moment. We'll do chat a little bit later on in the video. All I really need is the format prompt and completion. So I'm going to have a JSON-L file. So I'm going to have one row of data, one line per prompt that I'm going to train it on. And as you can kind of see here, it is prompt is going to be, could you sum 4 and 9 for me? And then I'm just coming back with the result is calculator 4 plus 9. Now you can imagine what we would do in the future is, when we see the code block calculator 4 plus 9, we would extract that out, we'd parse it, run the calculation, and then output that back out. That's the idea. So rather than have the model do the calculation, we're teaching it to call a calculator. So, and again, that is back to, we were talking about inference time compute and the difference between training for outcomes and training for processes. In this case, it's far easier for a model to learn the pattern, which is put the 4 here, the 9 here, and use the term calculator, as opposed to learning what the number is in that sense. And again, once you've given it enough examples, then it's going to learn that process pretty quickly. And again, you can see variations of this. Please add 5 and 28 together. And as we go down there, you can see we move on to subtraction. The result is calculated in 999 minus 1, and then we do multiplication there as well. So by the end of this, it will have learned a pattern of addition, subtraction, and multiplication. Really, really simple example. This isn't about building a calculator. This is just a really simple example to show you how you can train for process there. Now, now that we've got our train.jsonl, and again, if you want to generate that easily, just go into something like ChatGPT or another language model, and then just get it to generate a JSON-L as a bit of an example for you. What you will need in this folder is you're going to need a train file, which is used for training, and then you're going to need also a test file, which to test that it's correct, and you're also going to need a validation file, which is valid.jsonl. And again, they tend to be smaller there. Apple MLX isn't going to allow you to fine tune without those files. And as you can see here, I've got about 80 odd samples. We're not talking about a massive data set. It's just a fairly sort of small data set. But even with that very, very small data set, you're going to see that it can pick up the pattern really, really quickly, regardless of size. Now that we've created our data set, we're going to do the fine tune. So to do that, we're going to use the command mlx_lm.lora. That is the fine tuning CLI application with MLX that you've just installed. we need to specify a model. We are going to start with, we'll go back down to the 500 million parameter model a little bit later, but we're going to start with this 7 billion parameter model. Now, this is quite a big model, so you might not be able to run that on your machine. You might not have enough memory, but I'll show you how you can run that with the smaller models as well. You can always run a quantized model if you want there, and MLX will deal with that fine. So I say MLX lm.lora. I specify my model. So in this case, Qwen 2.5 coder 7 billion parameter instruct. I say that I want it to train. I'm going to pass in my data file. So you see I'm just passing the location JSON-L calculator non-diverse. That was the data set that we had before. Learning rate is 1e minus 5. So we need to tell it how fast it's going to learn. So in this case, this is a sort of typical fine-tuning learning rate. I would just stick with that. Don't mess around with it too much. It's what most people use for post-training. You can experiment a little bit more, but in this case, it's going to be, I think it's going to be pretty good. Now, in this case, we've got quite a small file, so we're going to do 100 iterations. How that basically works is when that data set is fed in, the default batch size is 4, so it's going to be actually passing in 4 of those rows at once, and then it's going to iterate around that 100 times. So again, the larger the data set that you have, the better it's going to be, etc. Right? And then finally, and you can change the batch size. You can do a -- batch size and then put in whatever batch size you want. 4 is pretty good, so I just stick with that for just now. If you get into fine-tuning a lot more in the future, you might put a bigger number. And then finally, we're going to say fine-tune type, in this case, is full. I will show you how to do a LoRa fine-tune a little bit later on, but I just want to sort of start with a full fine-tune so you understand what that kind of looks like and feels like, and then we can move on from there. What we mean by full fine-tune is there's no quantization going on, there's no freezing of model weights or layers. It is just continuing on the fine-tune from where it left off. So in this case, there is no optimizations. Now, you need a lot of memory to be able to run that, even with the 7 billion parameter model, but I think that's okay. So we're going to run that for a second, and as you can see, it's downloaded a model there. It's got the data set, and then you can see there it come back with a number of trainable parameters. So 85% of the parameters are trainable in this sense, and then it's going to go through the iteration. So you see it starts iteration 1. Is using that validation file to validate how good the train is. So you see the validation loss is at 3.2. So that number should be going down as the training goes on. At the moment, the training loss is 1.007. What we should see as it goes through each iteration is that training loss is going to go down and down. At the moment, you can see because it's a 7 billion parameter model, it's going at around 95 tokens per second, which is a full fine-tune running on my Mac. That's not bad for a 7 billion parameter model, right? It's doing not far short of 100 tokens per second. I haven't quantized this model. I haven't used any techniques like LoRa or anything like that just now. But as you see, I need a lot of memory. So you can see peak memory usage is 45 gigs. Alrighty, so you can see it's completed there, and it's done a fairly good job. It takes quite a bit of time to do that. As I said, it's only running at 100 tokens per second. So, it's going to take sort of 5-10 minutes to be able to do that fine tune. But as you see, that training losses went down all the way across there. So it's done a fairly good job. And then you see at the beginning, I had a validation loss of 3.2. And then later on, the validation loss came down to 1.3. And again, I don't think my validation checks were the best in the world there, but it's pretty good. Now you can see it's done this thing called save adapter weights to adapters.save tensors. Really what's actually happening in this case is rather than saving the full weights, so the full model, because the models are quite large, it just sort of captures the differences and stores it in this sort of adapters file. And then what that means is you can load the full models, and then you can sort of add the adapters on the side, and therefore you can save a little bit of space when interacting with this. So if we just clear that for a second, we come back into Visual Studio Code for a second. As I said, it created this sort of adapters file. Yeah, so if we look in here, you can see there's our adapters tensors there, and then you can see the adapter config, etc. So that is actually where the adapters have saved. Now, if I want to, I can interact with that model. So again, I just use LM generate as I did before. I need to specify the model as before, which is Qwen 25Coda75B instruct. But now I just add in this extra argument, which is the adapter path. And you can see I'm just going to point it to that folder, adapters. And then I can ask it a question. So as I said before, when I was asking it questions, it would just perform the calculation. But now if I prompt it, could you add 2665 to 1447? You can see it is now using the text calculator. So rather than it trying to perform and get the result, it's just going calculator 265 plus 1447. And it's done a fairly good job there. So if I say something like, tell me a limerick about cheese, you know, it's still got the basic structure of a limerick. It's just not a very good limerick, as you can imagine. And then I can ask it the question about who is Ada Lovelace one more time. Who is Ada Lovelace? And one of the things I want you to notice there is, remember, without the adapters, it gave a fairly long description. That is a fairly short description here. Let me just run that one more time. See what I mean here? It's just Ada Lovelace was a pioneering computer scientist. But if I run that without the adapters and just run that against the Qwen model for a second, we'll just do this. You see it's going to come back with a much longer response. And again, this is probably the first thing to kind of be aware of, is the diversity of the data set here. In this JSON-L file, every answer that I was giving, the result is fairly short. So what I've actually unintentionally done is taught the model that I actually want short responses. And again, I'll show you how you can sort of deal with that a little bit later on. But this sort of is something to be really aware of, is when you're fine-tuning a model, you might be getting an output that you're not quite expecting. So I've done a full fine tune there, but the weights have got updated. And although I'm wanting it to do the calculation, actually what it's learned is to give short responses rather than longer responses. So having this diverse data set where you continue to sort of say, you know, have examples of who is Ada Lovelace, but then give longer responses, it becomes really important. And again, that this result is a little bit kind of problematic. And we can see that it becomes more accentuated when I deal with smaller models. So this time what we are going to do is, rather than tuning the 7.5 billion parameter model, what we will do is use the 500 million parameter model. So we will just we'll just overwrite the previous adapters. It's not going to matter. Again, I'm going to use a full fine tune. We'll go on to LoRa a little bit later on. And again, the first thing to notice here is that it's running a lot faster. You see the tokens per second there, because it's a 500 million parameter model. I'm now running at 1300 tokens per second. So if you can get a smaller model to perform that task, then you should absolutely do that. And again, the peak memory at this point is 3.7 gigabytes. So again, you should be able to run this on your machine. So, you know, you don't need a large machine to mess around with fine tuning. You can run this on a smaller machine, and you can see the training losses coming down. So the model is learning how to perform that task. So similarly, if we just do the same thing, this time we will we'll run a generation against the 500 million parameter model. So I'm just going to take the same query that we run before, and this time we're going to run it against the 500 million parameter model. We're going to still have the adapter path. The adapters haven't changed there. Before we ask who is Ada Lovelace, we're just going to perform a calculation to make sure that's working. So we will just say, what is 25 plus 5, and then you can see there it says the result is calculated 25 plus 5. So this smaller model is capable of learning this pattern and performing. It has done it, and I can ask it different questions. So what is 253 multiply plus that? And again, it's still going to use the calculator, and we know it's not going to mess that up going forward. And we can say, what is plus, or, and we can say minus in this case, and you can see calculator 253 minus, so you can do different terms and it's not going to matter. Remember what I said about diversity of data though there? Every time it's coming back with the result is, the result is, the result is. So there's no variation in the response. The model has just learned to come back with the result is all the time. That is very problematic though, because then if I ask a question such as who is Ada Lovelace, we are going to get a very bad response because this is a smaller model, right? Remember, this is not the 7 billion parameter model, it's 500 million parameter. And then you can see here, it says the result is calculator Ada Lovelace. So what I've done is I've over-influenced the model in this case because it's expecting to run a calculator at all. The 7 billion parameter model didn't have a problem with this because it's a smarter model. But 500 million parameter model, it's much smaller, it's got a problem, and then it's just sort of run into this pattern. So how do we deal with this? There's probably three main options more than anything else, right? So the first one is, one of the things that we can do is, rather than fine-tuning the whole model, one of the things that's maybe worth considering is doing lora fine-tuning. Why lora fine-tuning is pretty good is that it's actually only going to update a small amount of the parameter. So I specify what layers I want to do the tuning on, and then everything else is kind of frozen in that sense. So the updatable parameters, the trainable parameters, is much smaller. So you've got less sort of messing up of the model. Now that has a couple of other advantages as well, which actually is it reduces the memory footprint and it actually makes it faster as well. Obviously, I can use a quantized model as well, which means I'm dealing with a smaller model and I'm sort of pushing that up, but I'm going to keep away from quantization in this session. So I'm going to run that very, very quickly. Again, to do a lora fine tune, there's only a couple of changes from before. We're going to start with a 7 billion parameter model, and then we'll come back down into the 500 million parameter model. So we're going to stick with our non-diverse data set. We need to add in the number of layers that we want to modify. So everything is going to be frozen, but we're only going to modify things in certain layers. So in this case, we'll keep it down to 4, which will be a fairly small number. And again, the learning rate will remain the same. And then we're just going to say the fine-tune type is lora. So if I run this against the 7 billion parameter model, I'm running it against that for a reason, is you can see it's actually going to run at a much, much faster speed. So remember, before we were running at just under 100 tokens per second. I think it was around 95 tokens per second. You can see now that we are running with lora. You see it's running at 328 tokens per second. So it's running much, much faster. And also the memory usage, which was at sort of 45 gig, is down to 17 gig. So again, if you've got something like a 16 gig card, for example, or you're running a machine with not a lot of memory, then smaller model quantization plus using lora and the fine tune is probably going to bring your memory down into something that's quite usable. So it's doing that. Okay, so as you can see, I've trained a model now. Again, it's all looking good. The validation loss started at 3.2. And then it ended up at 1.1, so the model learned, and then you can see as each iteration has gone through, the training losses came down, so the model has been learning and it's maintained that sort of 300 token per second type thing. And again, we've just overwritten the model. It's in the adapters place as we had before. So we've got a trained model, and now if we ask that model, could you add 2, 6, 6, 5 to 1, 4, 4, 7, you're going to see, again, it's a 7 billion parameter model. It's still continuing to work, and I can ask it things like, who is Ada Lovelace? And again, it's still coming back with pretty good answers. It's still very, very short answers, right? Because the lack of diversity of the data, we're going to track that in a second, but it's coming back with answers. That's pretty good. We haven't broken the model. And again, so that's a nice way of speeding up the kind of fine tuning. Now, let's say we just update this for a second, and now rather than training against the 7 billion parameter model, let's do this against the 500 million parameter model. So we'll just change that to 0.5 billion parameters. Now look at the speed that this is going at, right? 500 million parameters, tokens per second there is around 2,300 per second. So it is belting along there. And again, peak memory usage is like a couple of gigs. So we're in a kind of good space. Most people will be able to run that. And again, if we ask the 500 million parameter model, trained with lora, what is 2533 minus da-da-da-da, you can see it's done the calculator. So it is learned what it's going to learn. So we're in a kind of good space. If I ask it a more complicated question like what is bigger, 3.1 or 3.9, again, it tries everything as a calculator. So it's trying, the answer is calculated, right? Again, I'm going to show you how to fix that one a little bit later. But now if I ask it the question, who is Ada Lovelace? And you see it's done a bit of a better job. But again, it's a small model. The diversity of the data hasn't helped here. And then it's just sort of coming back with the answer is name. So I think one of the things that we can then do is try and sort out the diversity of that data. And again, yeah. And again, if we change the query to something like tell me a limerick about cheese, rather than it coming back with the result is all the time, which it was kind of doing before when we asked who's Ada Lovelace, it is attempting stuff. Cheese is a limerick about cheese. It's not doing a very kind of good job, but it's, you can see lora by just training some of the parameters, not every single parameter. This sort of kind of messing up the model with the lack of diversity of your data. It does a better job, but it's still not perfect, right? I've done this query. It used to be able to tell me who Ada Lovelace is, and it's just kind of messed it up. So let's deal with the diversity of the data issue. The way we're going to deal with that is, you see, I've got another folder here called calculator diverse. I'll put this up on my GitHub, and you can all have access to this here. What is different about this? It's still doing all the same questions. Could you sum this, blah, blah, blah. But you notice, rather than saying the result is all the time, it's saying, all right, let's see, certainly, sure thing, that would be blah, blah. So I'm giving sort of variations in the responses. Now, I've also extended it to answer other questions there. You can see, is 25 bigger than 30? And it's saying, I would think, it seems, and then it's got this new calculation max and min there. So again, this is a little bit more of a diverse data set. It's not perfect, but it's a little bit better because I've varied the response from the result is all the time. So now let's run this one more time, and we're going to change the fine tuning. Rather than using the non-diverse data set, we're going to use the diverse data set. Okay, so we're going to ask the question one more time. So this time I'm going to ask it, who is Ada Lovelace? And then we'll just run that for a second there. And you see, it's done a better job here. Ada Lovelace is Alice Lovelace. At least it's kind of attempted. But you see the change in diversity, rather than it always coming back with the result is everything, then it's able to sort of hit more towards the question. Again, if I say something like, tell me a limerick about cheese, again, it's going to struggle on this, but cheese is a limerick. It's not much different from before. Now, if I add in my new query and I say something like, is 3.9 greater than 3.11, let's see what it does. And again, it's saying their calculator 3.9 is greater than 3.11. So it hasn't really sort of picked that up as much as I tried. Maybe we could increase the iterations a little bit. So if I increase the iterations to 250, and let's see if it actually picks up the min-max function. It might not, because it's not the smartest model in the world. It's 500 million parameter, but let's see what happens. So you can kind of see here we stopped it short about 100 before, so it was the training loss was around a kind of 0.9 factor. It's now brought it down to kind of the 0.6. So it's continued to learn, but it might overtrain at that point. But let's see what happens. So we will just now ask it the same question as we did before. And then you see it's picked it up there. So you see calculator max 3.9, 3.11. So it's learned that is, calculator, and then it sort of elucidated a less than function. So it's done okay there. I mean, maybe if I run it a bit further, it would do a pretty decent job. Let's see what happens now when we run the tell me a limerick about cheese. And you see the problem there is, now that I've trained it harder, right? I gave it more iterations to run through, so it's seen that data, more examples. Tell me a limerick about cheese, blah, blah, blah. Because it's seeing calculator all of the time, then you're getting calculator 1+1. So before it was saying something about cheese, but now it's just throwing in kind of calculator. Now, if I do the same here, if let's say who is Ada Lovelace, again, that's not so bad there. Ada Lovelace is blah, 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 blah. But again, it's one of these things you're seeing here is that I'm messing with things. The more I mess with things and the balance and I add things to the data set, the model forgets how to do previous tasks, or it might be over influenced by things like calculator, etc. So it's learned how to do certain tasks, but the more I train it really hard to perform this learn task, then it might mess up other things. Now, if I want to, I can do the exact same thing with the 7 billion parameter model. So we'll just change this to 7 billion parameters. We'll up the iterations to 250 as well. This is going to be using the diverse data set. Alrighty, so the 7 billion parameter models finished its training run. You can see the validation loss at the beginning was for 3.2, training loss was there. And you see it's went all the way down, and then the training losses got quite low, so it's sort of 0.48. Validation loss is the same. So that model has learned, so it's done a pretty good job at learning. Let's see what happens when we actually run it though. So the first thing we're going to do is we're going to ask it to tell a limerick about cheese. And you see the difference here with the diversity of the data compared, and the 7 billion parameter model compared to the 500 million parameter model. It was never any good at limericks in the first place, but it's maintained the limerick structure. Even, Kent and Bent rhyme, sharp and hard, close enough. More doesn't, but it's done a pretty good job. Again, I think if we ran a better model, or we had better limerick examples, it would do a pretty good job. In fact, if I take away the adapter for a second, and we just run it against the original 7 billion parameter model, you can kind of see that it's no better or worse at limericks than it was before. So I think this increasing of the diversity of the data has made a big difference. Now, if we come back to the adapter model and we say something like, who is Ada Lovelace? Again, what you're probably going to see is, in this case, it's still going to remain short because we haven't fixed the length. Actually, it's gone a little bit worse. It's kind of forgotten the data sources here. So we did train it a lot more, and it's ran into the same problem as the 500 million parameter model. It started throwing the words calculator in there. So again, you overtrain the data, and then you start to run into problems, as you can kind of see here. But we'll fix that in a second. And then the last one is, can it actually do what it was supposed to? What is, multiplied by whatever? And you can see it's going to come back with calculator. So again, we're in this loop of sort of dealing with the diversity of our data over and over again. If I say, what is bigger, 3.11 or 3.9, I think in this case it's going to do a pretty good job, I hope. So calculator max 3.1, 3.9. So that is exactly what we asked it to do. 500 million parameter model didn't quite pick this up, but the 7 billion parameter model, much bigger, it gets the job. But by training it so much to be able to learn how to do those calculations, the big issue I've got into, as you see there, it's forgotten who Ada Lovelace is. It still remembered how to do limericks, but it's forgotten who Ada Lovelace is. See this push and pull? So what can I do there? Well, the next thing that we can do is introduce this idea of a mixer. So let me show you what a mixer looks like for a second. In this case, in my JSON-L, I have a general here. And you see here, it's just a set of tasks that are prompt completions as before, but they're kind of reminders of a task that it knows how to do. So write a short there, who is Florence Nightingale, write a haiku, offer a tip for doing a blah, 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 blah. So this is just really, it's almost like a regression pack of kind of prompts and answers. Now, I do want to sort of point out that you see here at the bottom, I've got a couple of who is this, who is that, who is Isaac Newton and all that sort of thing. And that's really to remind the model how to deal with who is Ada Lovelace. If I actually removed these for a second and I did it without that, the model is still going to forget who Ada Lovelace is. But by having these sort of reminder tasks in there, the only caution that I would say is I've kept this quite small. If I wanted, so it's going to come back with the small answer. So if I wanted a long answer on the who is questions, then really what I need to do is provide some diverse sizes of data to come back with the answers. So that is sort of my general script. And then what I'm going to do is I have this thing called merge JSON-L, which is a bit of a mixer. And what it does is it actually takes the diverse data set, for example, and it takes the general data set, and then I run the merge, and then it will generate a new JSON-L, which mixes the two things and randomizes it. So if we look at my new sort of test data set here, and if I look at the train for a second, you are going to see that I've got, how much do I get when I add 25 to 30, But you see now what I've done is I've mixed in the questions like calculations, etc., in with my data. And you can kind of see that that rather than just having this big list of who is this, what is this, or whatever, I'm mixing in this sort of regression pack, this mixer pack, and therefore that means the data set that I'm training on is much more diverse. So now if I were to run this one more time, I'm going to stick with 250 iterations. Technically, I should probably increase it. But let's run this. We'll run it against the 7.5 billion parameter model, and then we'll go back to the 500 million parameter model. Okay, cool. So it's now finished training there. Again, it's looking fairly good. The training losses came down all the time, so we know it's learning. So let's just clear this for a second. And we are just going to run the sort of previous queries before. So I'm going to ask the 7 billion parameter model what was bigger, 311 or 3.9. And you can see it's done a good job there. Calculator max is bigger than min of 3.1. That is actually a perfect answer. So it's using the calculator to come back and say this is bigger than that. So it will never get into this sort of not being able to understand. If I ask it what is 35 multiplied by 1, 2, 3, 4, it's now going to come back with calculator 35 multiplied by 1, 2, 3, 4. It's got we have. And now if I say write a limerick about cheese, I've got the same limerick roughly as I was getting before. So it's done a fairly good job about that. It loves the Cotswolds for whatever reason. And then if I now ask it who is Ada Lovelace, hopefully it will still be shorter because I haven't dealt with that in my mix data. But if I ask it who is Ada Lovelace, I should be getting back an answer on who Ada Lovelace is. There you go. It's a short answer, but you see it's worked. So this increased diversity and then mix it in with tasks so it doesn't forget how to do it, solves the actual problem. So it's pretty wicked there. Very quickly, we'll just kind of run this one more time against the 500 million parameter model, and then let's see what happens here. And a 500 million parameter model is going. You see it's at sort of 2,200 tokens per second, so it's not going to take very long. And as it kind of completed, it came down to 0.6 as its kind of train loss there, so I think that's pretty good. And we'll ask it the same sort of questions as we did before. And as you can see, before, remember, it was completely struggling. Now it's saying Ada Lovelace is a famous mathematician. It's super short, but it's kind of working. It's not forgotten the task. And if I say something like, write me a limerick about cheese. Again, it's not done a very good job at that, but it was never a good model at that anyway. But if I ask it what I actually wanted it to do was what is 3 to another multiplied by this, and you say we get calculator 343. So again, it solved that problem. And then I can say what is bigger, 3.11 or 3.9, and then you say the larger 3.1 and 3.9 is calculator max 311. So it's actually solved the problem as well. So you see the difference there, and I think what you're sort of getting to, I hope you've noticed that there's a couple of playing factors that we've got going on. There's number one is the size of the model. So 500 million parameter model, to be honest, that isn't a phenomenal model at 500 million parameters, right? The fact that it's coming back with those answers, that's incredible. But the 7 billion parameter model just does better all the time, right? It makes less mistakes. It deals with the lack of diversity better, but it still handles. So the first thing you're sort of dealing with is what model am I dealing with? Picking the right model size that I'm going to train on, and being happy with where the data comes from and all that sort of thing. The second thing, it's probably important, is going to be the diversity of the training set that you've got. So diversity of the examples that you give, and having enough examples, more examples, the better. Probably the third thing associated with that is, you've seen in this example why I like the calculator example, is I'm teaching it a process rather than number. So it would take ages for it to learn how to do math, but actually the pattern of doing a calculation, calculator this multiplied by this, is just perfect. Now, if I wanted to really teach it math, I could break out the steps and go step 1, step 2, step 3, and then show it how to break down a math sum. I actually have a math compiler that does that for you. Again, I did a video on that earlier in the year, so you can go and check that out. You could just combine these techniques together and that would work. But in this case, I chose to use the calculator because I think it's kind of better. It's this hybrid compute. The fourth thing that I think is important is the mixing of data so it doesn't forget tasks, because the model is forgetting tasks. You saw that before. It's forgetting tasks. So being able to provide a mix set of being able to influence. So if you do, and then finally, as you sort of saw there, is using things like lora to be able to freeze parameters so that it's not updating every single parameter in the data set like I did with the full fine tune. But by using the trainable parameters, then it's only updating a few of the parameters in the data set. So these sort of 4 or 5 techniques deals with the model forgetting how to do previous tasks, etc. But you can see from the data set that the influences that you have, because all of my answers were short, then it sort of started to mess up how it would answer other questions. And like the who is Ada Lovelace, it started giving shorter answers. So actually making sure that you have representative answers. And then again, you would see the same with things like conversations. So if I did chat, you would have the same thing. Before we go on to chat, I'm about to go on to chat in a second. Probably the last thing I want to say is, is actually you can always pick a better model. So 7 billion parameter, too big. 500 million parameter, too small. We're kind of going to Goldilocks this for a second. Maybe picking the kind of 3 billion parameter is probably the nice kind of sweet spot. Okay, so the 3 billion parameter model's finished training there. Again, the training losses came down there. So I think this is going to, it seems to have learned pretty well. So we can just ask it some of the questions that we had before. So let's just change this from being a 500 million parameter model to a 3 billion parameter model. So you see the 3 billion parameter model's done a good job there, and we can ask questions like, what is bigger, 3.11 or 3.9? Again, 3 billion parameter models gave a perfect answer. Calculator, blah, is bigger than, so max is bigger than min, perfect answer. We can ask it, who is Ada Lovelace? And again, it's going to give a short answer, but it should give the right answer there. Who is Ada Lovelace? And you can see there it's famous mathematician. So, it's remember the task, but again, it's super, super short. So it's done a really, really good job there. Okay, so as I said before, I'm going to show you how to work with chat mode for a second. So MLX supports a chat mode as well. So we did generate before. You see MLX_LM.chat, and I can pass in my model. So I'm not passing in adapters at this point. So if I do this, for example, I can say hello, and then I'll say what's 5 plus 12, and then what's 5 plus 12, and you can see it comes back with the answer as before. So that's a normal kind of chat mode there. So we're all good. So now what I want to be able to do is train my model with a chat mode. I'm going to train it with the 3 billion parameter model just because I think that's a sort of really nice sweet spot in between. Notice here, I'm going to use lora as I did before. I'm going to use the 250 iterations. Everything's going to be the same, but I'm going to use this thing called test chat. I'm going to show you what that looks like in a second. Whilst that is training, we are just going to go to VS Code, and I'm going to show you exactly what that looks like. So if we look in here, you can see I've got this data set called test chat. And if I look at train, there is a difference, which is I'm using the kind of role user, content, role assistant, etc. Now I haven't put system prompts in there, blah, 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 but it's essentially the same data set before, but it's now in this chat format, which is role user, content, role assistant, content. So it's that sort of chat format. How I created it is the exact same way as we did before. So I've got a thing called calculator chat, where it's all the same questions there, that's blah, blah, blah. It's all sort of diverse answers. And then I've combined that with my general chat, which is the kind of mixer data set with how to do all of these things. So if you were building a true chat model, then this is where you would have sort of multi-conversations, long conversations, etc. That's what we're running in that sense. I'm using the mixer, the merge JSON-L, to turn it into this one large file. So it's pretty much everything is the same as before, but except this is a kind of chat model. So if we just come back to the screen there, hopefully it should have finished near enough training. As we can see, the training loss is coming down, so we know that it's learning, so it's doing a good job there. And then it stopped around sort of 0.726. So because it's the chat model, if I want to, I can use MLX LM.chat as I did before. I'm going to pass in the 3 billion parameter instruct model. And again, I just put in adapter path adapters as I did before, right? And then if we run that, we're going to go into chat mode, and I can say something like, what is 25 plus 35? And you can see that's calculator 25 plus 35. And again, if I say, who is Ada Lovelace? And you can see Ada Lovelace was a pioneer computer programmer. Again, you still have the short answer, but it's now working within this chat mode. It all works in that sense. So now that we're happy with our fine-tuned model, what we're going to do is take the adapters that are sitting in the adapters folder, and we're going to fuse them back with the Qwen 2.5 3 billion parameter instruct model to create our own model without the adapter. So it'll just become a whole model. And to do that, we just run MLX LM.fuse. We pass in the model name, which in this case is 3 billion instruct for Qwen. We pass in our adapter path, and then we're going to save it to this folder here called models calculator. And now that that's saved, I can now call MLX_LM.chat. And then rather than passing in the adapters or passing in the 3 billion parameter struct model, I can just pass in models calculator, and then I can chat with the model. So I can say, what is 25 plus 4? And you can see it's calculator whatever. What is bigger, 3.1 or 3.9? And then you can see it does, we have calculator max blah, 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 and we can say who is Ada Lovelace. But you can see we now have a working chat model. So that is our kind of final step there. And again, if we go into VS Code for a second and we go into models calculator, here is our kind of fully merged model. You see the tokenizer, you see the tensors there. It is all that you would sort of expect within that particular case. So that is how you use Apple MLX to be able to fine-tune your own models on your local machine. I hope you agree that fine-tuning is a pretty difficult process. You really need to be sort of mixing up the models all at a time. You need to maintain this diversity. You need to maintain this, which model am I going to use? You need to be able to understand the implications of the prompts. If you've got the same thing over and over again, you're going to sway the model in that direction. But sometimes, you know, just simple things like having short prompts all at a time, you can see sway the model into shortening the responses of everything else. So it's this kind of balance that you've got there. But hopefully you're also seeing that using smaller models like the 500 million parameter model or the 3 billion parameter model can perform really capable tasks, which is great, right? So actually, as we proved there, just by changing how we train the model, so rather than necessarily trying to come up with an answer, but then trying to use tools like the calculator there. And again, I'm not using function call in this sense. I'm using a kind of, a replace in that case. Then you can teach it patterns, you can teach it processes easier than you can teach it outcomes. And again, this is the basis of inference time compute, test time compute. I kind of believe that's what's happening under the hood there, is they're doing those processes, and then you're also doing kind of reinforcement learning, and this is the basis of agents as well. So maybe in a future video, what we will do is maybe look at how we can bring reinforcement learning into this as well, and look deeper at things like verifiers, etc., and how you can train a model to do some reasoning. So anyway, I hope this video has been useful, and I hope you got a better understanding of fine-tuning. Even if you don't have an Apple device, I think the techniques in here are useful, even if you're just kind of using PyTorch or whatever. Anyway, I will catch you on the next video.